What's up, guys? I'm Chad Barnes, and welcome to the channel. Here, it's all about real car talk, from simple fixes to smart driving tips and keeping your ride in top shape. If that sounds good to you, go ahead and give the video a thumbs up. Hit that subscribe button and make sure you watch all the way through. There's a lot of good stuff coming. Let's get to it.
It's all about the contradictions inherent in the very essence of car tires, because the tire must connect the car to the road and separate it from the surface on which the car is moving. It must be soft and resilient enough to effectively absorb bumps, and stiff enough not to deform too much and impair handling. It must be sure to cling to the roadway, because otherwise the car will not be able to move forward, pushing the tires off the road, or stop when it is necessary for the driver. At the same time, the tire must have minimal rolling resistance so that the car does not use too much fuel, and this can only be achieved by reducing deformation, and it must not wear out too quickly. Try to combine high traction, low rolling friction and low wear. These requirements are called magic triangle in one product. It is clear that the properties of a particular tire model determine the combination of tread pattern and internal structure. But anyway, everything starts with the composition of the rubber compound. And now let's remember what rubber is in general. It is based on rubber. This natural polymer has one problem. It is elastic, but quickly oxidizes in the air and becomes brittle. In 1839, Charles Goodyear discovered the process of vulcanization, discovering that a heated mixture of rubber and sulfur turns into an unusually dense elastic material, much more stable than the original fusible polymer mass. And it turned out because sulfur, attacking the double bonds in the rubber molecules, creates so-called sulfide bridges, strong bonds that connect neighboring chains of rubber and form a mesh structure. Basically, from a chemical point of view, the entire rubber mass is a single molecule. In 1888, John Dunlop, trying to improve his son's bicycle, created and patented a tire made of vulcanized rubber, and in 1895 André and Edouard Michelin installed rubber tires on a car that participated in the Paris-Bordeaux-Paris race. Thus was born the automobile tire, which began a victorious march across the planet that continues to this day. But the composition of the compound used to make modern tires is much more complex. It still often includes natural rubber. For a number of reasons it cannot be completely replaced. The fact is that the side chains of rubber molecules hang strictly on one side of the main chain, and although methods of industrial production of artificial analogues have long been discovered, by the way, the priority in this matter belongs to the Russian chemist S.V. Lebedev, and although the methods of industrial production of artificial analogues have long been discovered, by the way, the priority in this matter belongs to the Russian chemist S.V. Lebedev. V. Lebedev. It is not possible to achieve such a structure in artificial polymers. The control over chain assembly, which is provided by complex plant enzymes, cannot be repeated in reactors with much simpler organometallic catalysts. In addition, the natural base for natural rubber is limited and there is simply not enough of it to meet all the needs of mankind, in rubber in general and in car tires in particular. As a result, the share of natural rubber in modern tires is at best 10 to 15%, and at least 20% is accounted for synthetic polymers. Polyisoprene, polybutadiene, copolymers of polybutadiene with polystyrene and polyisobutylene. However, recently, more and more often there are tires made entirely of synthetic rubbers. The progress of chemical technologies does not stand still, and the economic reasons are affecting. Artificial rubbers are not only more resistant to oxidation and ultraviolet radiation, but also banally cheaper. In addition to rubber, the tire compound must include carbon black, simply put, industrial carbon black. It gives the tire mechanical strength and wear resistance, because it provides good molecular bonding during the vulcanization process, and at the same time and familiar to all the black color. An important component is silicon dioxide, aka silica. It is responsible for improving grip. Older people probably remember Soviet erasers of red color, in which even visually visible glass dust could be seen and with which it was possible to erase even written in ink, and together with the top layer of paper. And what is glass? It is silicon dioxide. And then it's the turn of various additives. Some of them are antioxidants, and their main task is to catch active oxygen forms dangerous for rubbers and other polymers. For example, ozone or peroxide, turning them into harmless water. Others, such as organic oils, are added to keep the mixture flexible at low temperatures. Still others, such as zinc oxide, act as activators of vulcanization. And all this complex molecular set must work in concert, in a single concert. It is clear that the leading tire companies spend huge efforts on the development and research of new rubber compounds, and one of the undoubted leaders in this regard is the Japanese company Toyo Tires. They were the first to put that empirical shamanism, which was the creation of new compounds, on a strict scientific basis. The complex of scientific methods that made it possible to create mixtures with specified properties and predict their behavior in various conditions was called nano-balance technology. To understand how this technology works, we must first understand what the nanoworld and nano-objects are. Today, nano-objects, nanoparticles, are objects, particles, with a characteristic size of 1 to 100 nanometers in at least one dimension. It is in this range that the sizes of polymer molecules lie. Well, to understand what 1 nanometer is, let's do a mental experiment. Imagine a car tire, increased in size to the diameter of the Earth's equator. So, compared to it, an object the size of 1 nanometer would look like a modern 1 ruble coin. It is clear that in order to study such objects, you need special equipment. And just as Anton Leeuwenhoek's invention of the optical microscope opened a window to the microcosm, the electron microscope invented by M. Knoll and E. Rusk provided access to the world of nano-objects. It happened in 1931, and scientists were finally able to see objects of submicron and nanometer sizes. That's when the Thomas the Unbeliever principle kicked in. Until I see it, I won't believe it. But the real era of nanotechnology came only in 1981, when the scanning tunneling microscope invented by H. Binnig and H. Rohrer gave scientists the opportunity not only to obtain images of individual atoms, but also to manipulate them. Toyo Prox TR1. These tools are still in the arsenal of tire companies' research centers, but they were still not enough. For example, consider the situation with the inclusion of silica in blends. The whole problem is that rubbers and other polymers are radically different chemically from silica and bond about as readily as oil and water. This means that when we simply mix the components, we will get separate large clumps of filler that stick together and separate areas of the rubber mass that have no filler in them. And now imagine that you try to make from such rubber, well, say, a rubber band for a slingshot. Firstly, it will not produce the expected throwing force, and secondly, it will tear very quickly, because it will stretch unevenly. And the boundaries of areas with different properties will serve as stress concentrators. This means that a substance is required that can coat the surface of silica particles and make it similar in its properties to the surrounding polymers. Such substances are, for example, BIS, triethoxysilylpropyl, tetrasulfide and its analogues. Their molecules consist of two parts, one of which readily binds to silicon dioxide and the other to the mesh of the vulcanized polymer. But even having such a substance, it is required to distribute it evenly over the surface of the particles, otherwise they will still stick together, because the molecules of the masking agent, alas, themselves lack the ability to independently aggregate. To study this process, Toyo Tire specialists used synchrotron methods, which allow us to see directly, at the nanoscale, how the material deforms. The Spring 8 synchrotron at the Riken Laboratory in Hyogo Prefecture was used for this purpose. This huge facility, the synchrotron ring is 1,436 meters long, can receive a beam of charged particles with energies up to 8 GeV. Such high energy allows deep penetration into the mass of matter and recording the processes occurring at the molecular level in the form of a movie. It was the study of samples at the synchrotron that made it possible to study the dispersion of fillers in the rubber material and the processes occurring in it during dynamic deformation. On the basis of these studies, a mathematical model describing the processes occurring in the rubber compound was built, and this, in turn, made it possible to abandon the blind selection of the main components and their proportions and move to a scientifically based design of materials for tires with the required parameters. Now Toyo Tire specialists work according to the following cycle. First, virtual experiments are conducted on a model, then a real sample is created, tested for compliance of real parameters with theoretically predicted ones, and, finally, the experimental mixture goes to the production of serial products. But even here, everything is not simple. Studies have shown how important a parameter is the uniformity of distribution and dispersion of the filler in the rubber material. In order to achieve the required indicators, it was necessary to develop fundamentally new technologies for preparing the mixture, and use highly precise methods of observing the ratios of all compound constituents. The fact that nanobalance is not just a marketing name, But a real way to achieve ideal results became clear back in 2011, when Toyo Tires for the first time managed to create a tire that received the highest AAA rating for low rolling resistance, and therefore, the highest environmental friendliness, and the highest rating for high wet grip. In fact, both traction and rolling friction are governed by the same parameter, the loss factor Tg sigma. Rolling friction is governed by the loss coefficient for low-frequency deformations in the tire, while traction is governed by high-frequency deformations. So direct attempts to increase traction by conventional methods will increase rolling friction. Well, and the use of nano-balance technology still allowed to solve this problem, which at first glance seems insoluble. The direct proof can be the parameters obtained by comparing the new Toyo tires with their predecessors. Toyo Nanoenergy van tires, for example. Toyo Nanoenergy van tires compared to its predecessor, Toyo H08, have a 29% lower rolling resistance, which, incidentally, means a 10 to 15% reduction in fuel consumption. At the same time, Nanoenergy van has a 10% shorter braking distance when braking from 100 km per hour. Another example is Toyo Prox TR1 sport tires. If we compare them with the previous model, Prox T1R, the use of nano-balance technology has made it possible to reduce braking distance on wet pavement by 16% and reduce rolling resistance by 10%. In conclusion, Toyo's innovative approach to enhancing tire performance has successfully achieved the remarkable feat of improving both traction and rolling resistance simultaneously. By leveraging advanced materials and cutting-edge design techniques, they have created tires that not only grip the road better but also reduce energy loss, leading to improved fuel efficiency. This dual enhancement not only benefits drivers with a safer and more economical driving experience but also reflects Toyo's commitment to sustainability and performance. As the automotive industry continues to evolve, Toyo's advancements set a new standard for tire technology, paving the way for a future where safety and efficiency go hand in hand.